Okay, welcome everybody to this last day of the PhD school. So we'll start the day off with Kai Yan's last lecture. So take it away, Kai.
Okay, thank you. Good morning, everybody. Welcome to the last lecture. Yesterday, on Wednesday, we talked about event shape and energy correlators. And we focus on computing these observables from on-shell approach, either from the on-shell scattering amplitude or from the super form factors in N=4 super young Mills. And we discovered some unexpected symmetries between different type of event shape observables, basically between the charge and the energy and scalar flow correlators. And today we would like to think a little bit further about the symmetries between these observables, and we will be studying these things from the offshore approach. We will introduce the methods and techniques to compute event shape observables from conformal correlation functions. And it is a systematic approach for obtaining the flow correlators in N=4 super young Mills. And in a way that we can bypass inverse singularities completely and do the calculation in 4 dimensions. And in the end, I will comment on how we can generalize this approach to the studies in QED or QCD. So let's get started. Well, yesterday I talked a little bit about the super stress tensor super multiplier, this capital T in N=4. And it can be obtained by performing super conformal transformation on the scalar half BPS operator O20 prime. Here 20 prime means it's the operator takes the representation, a certain special representation of the SU4 gauge group. So this operator is defined by a product of 2 scalars projected onto some harmonic SU4 harmonic variables YAB, or effectively these UA times UB. And you can, my notation is that if you contract one pair of these Y variables, then it is equal to like Yij squared. So in some sense, it's the same notation as the embedding formalism. It's a 6-dimensional vector contracted together is equal to some 4-dimensional, the 4-dimensional distance squared. So I said yesterday that the stress tensor multiplet includes all these conserved currents in N=4, including the R symmetry current J and the stress energy tensor T mu mu. And it also, it also contains the Lagrangian L as a certain component. So we can obtain and extract the, for example, the R symmetry current from a somewhat certain component of the stress tensor multiplet. So we basically can obtain this expression by performing a Q and Q bar supersymmetry variation on the scalar operator, half BPS operator O, and then expand this the expansion T in terms of theta and theta bar, and we can then extract a certain component in the theta and the theta bar to obtain either the currents, the R symmetry currents, or the stress tensor multiplet. This expression, this operator is a bit long here, so I did not write it down, but you can look it up from the literature. So that tells us that if we want to compute the correlation functions in equals 4, which are consists of the currents or the energies, we can simply start from the correlators involving the T, the stress tensor multiplet. So for the case where we have only two operators, like the 2-point and 3-point functions, are extremely simple because the superconformal invariants fix the form of these 2-point and 3-point functions up to a overall constant. So here it is the explicit expression. It is given by this, it's represented by these tree-level diagrams where the propagator is not the standard the scalar propagator, but it is the supersymmetric version of it. Basically, it's a xij is the normal like distance squared, and this y hat ij is given by these following expressions. So this particular form of these propagator guarantees that it is invariant under the supersymmetry, the Q and Q bar variations. So also for the 4-point case, it is no longer so simple because the 4-point function can receive loop corrections, which can depend on the conformal cross ratios. But at tree level, it's still given by these simple like tree level diagrams that are just products of these supersymmetric propagators, DIJs. So given these general formula, we can extract, depending on what observable we're interested in, we can extract the relevant flow operators from these correlators of the stress and energy tensors. For example, if we want to compute the scalar flow, a thing with single detector, then we can put this detector on this position x2, and there are two sources which are given by the scalar half BPS operators, which we put on at x equal x1 and x3. So we basically just need to compute these 3-point correlation functions of 3 identical scalar operators. And it is given by these 3-point supercorrelator by setting theta and theta bar equals 0. Remember that this O is the lowest component of T. So the T has this expansion like O plus theta theta bar J plus So the lowest component O can simply be obtained by setting all the thetas to 0. And doing so means that if you look at this expression, you simply throw away these terms and you get some standard product of propagators. And here these Y's are the products of the harmonic variables. I mean, the appearance of these Y's helped us to restore the complete SU4 dependence of these SU4 structures of the scalar operators. So yeah, it's in some sense it's bookkeeping if you are just interested in the kinematics, but it's helpful for you to restore the SU4 structure. So yeah, so you can obtain this 3-point correlator 3 O's by doing this simple replacement. But what if you're interested in a charge flow where you replace this one of the scalar operator by the the R symmetry charge J, and you can still start with this supercorrelators, and you act on these a set of differential operators which are given here. by super conformal word identity, then you can obtain this expression. So here you have a kinematic dependence is a bit more complicated because of the current J is spin 1, it has spin 1 indices alpha alpha dot. So this is the only conformal tensor which depend on one pair of indices alpha alpha dot, which you can write down. So you can like convert it into the four Lorentz four vectors notation, and it's maybe you're more familiar with this form, and you can check explicitly that this tensor transforms nicely covariantly under the conformal transformation, and it is neutral at point 1 and 3, and it transforms like as the a vector at point 2. So in N+4, we can see that the correlators all different type of currents can be obtained in a simple way, starting from the supercorrelator. And the result is takes a expected form, and the conformal structure is fixed fixed by the overall conformal transformation property of these operators. So the next step is to of course compute the correlation on the an event shape from the correlation functions. So there are a few steps that we need to do. First, we need to perform the analytic continuation from the Euclidean space to the Minkowski space. So far we have only been talking about correlators in Euclidean space, but in the end, we need to study the detector physics, which obviously lives in the Minkowski space. So how do we do the analytic continuation in a consistent way? So here we cannot just compute a time-ordered correlation function, which is the standard story if you compute the Green functions. But here our detectors and the operators are not time ordered. And in order to do the analytic continuation, we need to understand this approach called the Wyman prescription. So the idea is the following. So we start with the Euclidean version of where all the coordinates lives in the Euclidean space. And then we can do a wig rotation for the X4 component in the following way, such that all the X4 component acquires a small negative a real part, epsilon k, and an arbitrary imaginary part. And we require that we are living in a holomorphic sheet where these real part of the X4 after an analytic continuation is ordered from left to the right in this for the correlation function. So this guarantees that this is a single, after this analytic continuation, we still have a single value function. And the simplest example is the 2-point function. So in Euclidean space, you just get this standard propagator, but delta is the scaling dimension of the propagators. So after analytic continuation, you get a minus sign because of the Minkowski signature and a small imaginary part whose sign depends on the sign of T1 minus T2, where by convention, T1 is the one, X1 is the one that appears on the left, and X2 is the one that appears on the right. So So to summarize, the analytic continuation, by doing analytic continuation, you replace the xij squared by this modified propagator. So it has an imaginary part which depends on the difference between the zero components of xi and xj, where I is on the left and j is on the right. So this gives us the so-called Wyman function. It coincides with the time-ordered correlation function only in the region where this T1 is greater than T2 Tn. But not in the other regions. In the other regions, it differs from the time-ordered correlation function by certain discontinuities in certain channels xij. So the simplest example, simplest event shape or physical observable that you can compute from the correlation function is the total cross-section. So that's consider a process sourced by a scalar operator O. And by computing the total cross-section, normally you compute the Armstrong form factor or the cut diagrams and you integrate over phase space. But you can do it in an alternative way by computing the Wyman correlation function and then doing a Fourier transform back to the momentum space. So you can check that this Fourier transforms gives you this expression, which is positive and real. And it should be equal to what you get from computing the cross-section from the amplitudes. And this verifies that the way that we do the analytic continuation is valid. And so that's obviously this is a very trivial case where you do not have any detector insertions, only the source and the sink. But if you want to measure some charge or the scalar flow, you need to insert a detector representing by a flow operator. Here it is what it looks like. I have already given this form yesterday. So in general, the so-called the flow operator is the ON is given by a local operator with a certain spin and the scaling dimension delta, and then you should send it to the future null infinity, representing the situation where the detector is infinitely far away from the place where the local interaction takes place. And then you integrate it over the retarded time along the square plus plan, and that means you integrate over the detector's working time. So we primarily only consider the operator with twist 2, namely delta is equal to s minus 1. These includes the scalar flow, energy flow, and the charge flow. They have spin 0, 2, and 1 respectively. So the simplest case is, of course, the scalar flow operator. And the 3-point correlator we have just written down, it is just a product of 3 propagators. And here I put a hat because I already did the analytic continuation into the Minkowski space following the Wyman prescription. So now I would like to send the detector sitting at x2 to the future infinity. The way I do that is to perform a light cone decomposition. So I decompose this x2 into the 2 components, like x2 equals to x2 plus n plus x2 minus n bar, where n bar is an auxiliary vector, which is not collinear with n, and n is the direction or the angular direction where the detector is the angular it's the direction of the detector with respect to the left brane. So this is a null vector, so is the n bar vector. So after doing the light cone decomposition, we set this x plus the advanced time to infinity. And doing that, we simplify this expression for the x12 squared, and it factorizes into this plus component and the minus component. So here, please pay attention that the x12 squared contains a pole at x2 minus equals x1 minus, where x1 is the location of one of these scalar operators representing the source, and the pole of the location of the pole is in the lower half plan, in lower half complex plan in the x2 minus plan. And here is for the x23 squared, because the way we do the analytic continuation, it developed a pole in the upper half plane in x2 minus variables. So, in the end, we obtain this expression where we need to keep track of all the signs of I epsilon prescriptions. And the next we can integrate over the detected time, namely x2 minus. So it's here we only have a very simple rational function, so we can do it without any trouble. It is a contour integral having two poles on opposite side of the real axis. We can close the contour from above and pick up the pole here, and which gives us the final answer. So then so after integration of the detector time, we have a correlator of the three operators, which in coordinate space. It depends on these xij's and the direction of the charge, the scalar flow operator. And then we should do the Fourier transform. This is the last step into the momentum space. And how do we do it? Well, we can play some tricks. First, we can rewrite this propagator with n dot x in the integral representation using this Schwinger parametrization. And we combine these factor after the Schwinger transformation with the x squared. And then we do a Fourier transform with Fourier transform using this master formula. And in the end, we get the final expression, which is proportional to 1 over q dot n, where q is the center of mass energy. We can check that this answer is actually consistent with the conformal symmetry, because the scaling dimension and the spin tells you how the final answer should look like, and the rescaling of these vector n, as well as the rescaling of the center of mass energy q. So you can check that it is actually satisfy all these rescaling properties. So this is a simple example where I explained how the basic steps of computing the energy or charge or scalar flows from correlation functions. We are only dealing with the tree level computation. And for the 2-point or the 3-point, for the single operator insertion, single detector insertion, this is sufficient in n equals 4 superyon mills. because the half BPS operator is protected in the sense that the 2-point and 3-point function does not receive any loop correction, and the Born level answer is exact. This a theorem called BPS shortness. You can refer to like literatures that I give at the beginning of these lectures for detailed explanations. But starting from the 4-point function, it can receive loop corrections, which could depend on the conformal cross ratios. So if we would like to do the precision calculation of the event shape beyond the leading order, we need to first compute the correlation function, the loop correction to the correlation function. So how do we do that? And then the standard procedure is to compute the loop correction through the Lagrangian insertion approach. The idea is the following: if you want to compute the correlation function with certain insertion of the action, and you want to extract the order g squared term, and you can simply perform a derivative on the correlation function and then set g equals 0. All right, so what can explicitly depend on the which term can explicitly depend on this gauge coupling g squared? Well, it can only come from this action S, like D, which is the Lagrangian, integrated Lagrangian. So in Lagrangian, we can like redo a rescaling for each field, for the field strength operators, such that the only G dependence is in the Young-Mills Lagrangian, like given by F mu mu, F mu nu, G squared. So this means if you take derivative with respect to g squared, it is equivalent to inserting this Young-Mills Lagrangian into the 4-point correlation function, and then you integrate over the insertion point. So this.
Kai, there's a reference request in the chat.
Okay.
I see.
For the tree level computation of the 4-point or 3-point, which
the last, like the 4-point and well also the 3-point if you want, but yeah, the last one you made. Not
this
the one.
This
yeah,
one.
The tree one.
Okay. Yeah, there is a reference. I will like leave a message in the Slack channel.
Okay, great. Thank you.
Yeah. No problem. So this procedure is represented by this 5-point diagram, where it is a tree level diagram. But in the end, you need to integrate over the insertion point. So the tree level, the integrand of the 5-point diagram respects conformal symmetries, and you can compute it by either doing the Feynman diagram, honest Feynman diagram calculation, or use some advanced techniques of solving it from conformal anomalies. But you at one loop level, you sort of expect what the answer look like because of the conformal properties of these integrand. It must be given by this conformal one loop conformal integral. This is the only option, and it is integrates to the phi1 function that we're very familiar with. So this function depends on two cross ratios, U and V, defining the standard way. So the difference for this type of calculation is that when we do the analytic continuation and do the detector physics, we need to be a bit more careful because the phi1 functions develop branch cuts in various regions. So if we do not take care of the the I epsilon prescriptions carefully, it is impossible to manipulate this expression and do the time intervals and so on. So the way we treat it, well, the right way to do it is to do the analytic continuation for the cross ratios U and V, and then to do the and figure out what is the integration contour when you integrate over the detector times, and then take care of the branch cut structures of the correlation functions. So let me explain a bit more detail. So after you perform the analytic continuation, you can see that the correlation function will develop branch cut when the x12 squared is positive and x2 3, 4 squared is positive. These are the regions where the detectors are time-lag separated with respect to the source or the sink. Originally our integration contours goes from the x equals minus infinity to infinity. So we integrate along the real axis, but we can deform the integration contour such that it wraps around the two branch cuts in this way. And the integral, this twofold contour integral x2 minus and x3 minus, can be converted into a discontinuity in along this one branch cut. Well, that can, and well, there were twofold integrals, and for each of the integrals, you need to compute the discontinuities along a certain branch cut. So putting these things together, we find that the integral can be converted by a double discontinuities of these regarding the U variables, because you do a discontinuity in x12 channel and x3 channel separately, sequentially. So this means you need to do a double discontinuity with respect to at U equals 0. So after doing this discontinuity manipulations, the integral is converted to a twofold integration along these branch cuts, and the integrand is real and positive. So that integral is, first of all, finite, and also is unambiguous. And the integrand is manifestly real, and in fact, it's positive. So in the final step, so that after performing the time integral, we obtain the correlation functions in the coordinate space, which can only depend on the cross ratio gamma. So this is the only conformal invariant object that you can write down, which depends on the xij, which is the distance between the source and sink, and the two null vectors n and n prime, which represent the directions of the detectors. So in the end, this correlation function in coordinate space can only depend on the single variable gamma. And in the final step, we perform Fourier transformation into the momentum space, and that is that gives us the event shape in momentum space, which depends on Q and n prime, and the only conformal invariant quantity that you can write down is this zeta variables. And in center of mass frame, it is equal to 1 minus cosine n prime, where n and n prime are the are the angles, this cosine theta is the angle between the two detectors. So to summarize, I have introduced the approach and explained how it works to compute correlate and eventually from a correlation function. So by doing this computation, we do not need to do any phase-space integrals, and there is no summing over final state, and hence no IR divergences that are encountered. It certainly gives an advantage compared with traditional approach, and especially it is suitable for it is systematic approach that can be generalized to higher loop order. And the most challenging part is just to compute the loop corrections to the correlation functions. As long as we're interested in for super young Mills, this step is already the high loop corrections to the correlation functions. It's already studied extensively during the past decades, and many interesting results is already obtained and available. So, but the next question that we would like to answer is that can these approaches be directly applied to phenomenological studies, for example, for some observables in QCD or QED that are currently measured at collider physics. So then in the next part of the lecture, I will give a simple example, which is a Born level charge flow for a for a U1 charge embedded in a series with a global SU2. So you could, an analogy to this kind of charge is the weak isospin in electroweak series in the weak SU2. So the standard observable that we normally are talking about is the electromagnetic charge in QED. But however, in QED, if you just have three identical electromagnetic currents, they're all vector currents. Then there is this Fourier theorem telling us that the 3-point correlate vanishes for three identical vector currents due to the charge, both the symmetry and the charge and the parity and the charge conjugation. So we cannot just talk about these simple, two trivial examples. But we still can do certain studies for the 3-point charge correlators. If we consider a charge currents in weak SU2, so for the electromagnetic currents, we simply have this J mu equals psi bar gamma mu psi. But for this charged weak current, induced by the W plus and W minus. You can add an SU2 indices to this fermions, and also there's a Felicity projection. So this is no longer a vector current, it's a chiral current, and it also carries indices SU2. What we can measure is that we can choose a particular U1 charge in this setup. For example, we can choose this isospin given by this 2x2 matrices in the flavor. This A and B are the flavor SU2 indices, and so now each of these currents carries a SU2 indices A, B, C, D, and the detector the detector should be contracted with this matrices representing the charge that we measure at the detector. So this kind of by adding in all these indices, we can save that this quantity such that it does not vanish, and we can actually extract the parity even part by this particular choice of the charge and currents. So let's look into the details. So we would like to compute the Born level, this 3-point correlation function for the 3 chiral currents given here. So I have already projected this four-dimensional Dirac indices into the 2-dimensional wire spinners, such that this current is manifestly chiral. And we can derive the Feynman rules for this computation, which the only diagrams that we need is the propagated 2-point function for the 2 fermions. So you can first write down this expression in momentum space and then do a Fourier transform. So this just then P will become a derivative on X variables. So this is the Feynman rule in coordinate space. So then we would like to explicitly compute this 3-point correlator at Born level. So there are 2 diagrams that we need to consider. This is the clockwise, well, this is this diagram, the fermion flow goes clockwise, and in this diagram, the fermion number flows in counterclockwise directions. So this gives you 2 terms. You basically just put together 3 fermion propagators together. So there are some overall factors C1 and C2, which come from the this SU2 flavor indices. So we can write it down in a more explicit way. So for this diagram, we have so we consider, so suppose that for the current J1 mu, we consider the charge current with the positive, well, induced by the W plus. So this means we need to contract this J mu AB with some YAB, where YAB is given by this 2x2 matrix. And for the current at X3, we contracted with a different 2x2 matrix Y2 equals this. So here for this diagram, we just have a trace of Y1, Q, Y2. Remember, the Q represents is our measurement of the charge. And for this diagram, we just have trace Y2, Q, Y1. So if we pick the charge to be this isospin, we find that these two constants carries opposite sign. So we can say one equals 1, the other one is -1. And this indeed gives us a structure that preserves the parity. On the contrary, if C and C, these 2 constants are the same. For example, if you have the Z boson, that is the neutral currents coupled to the leptons, then these 2 diagrams will give you the same constants, and you need to subtract the second one from the first one, and that gives you a parity odd contribution, which then leads to the anomaly in the electron weak theory, if Z boson is concerned. But for now, we don't worry about that. We only focus on the parity even contribution. So these terms looks very complicated, but from what we learn from the n=4, we know that the correlator must be decomposed onto some conformal tensors. At least at tree level in QED or QCD, this is still the case. So what are the conformal tensors that you can write down where your currents carries 3 vector indices, mu1, mu2, and mu3. So here are the only 2 possible conformal tensor that you can write down, which preserves parity. So for the parity odd part, you have a third one, T3, which involves the epsilon mu sigma x sigma tensor. But now we only have 2. The first one is given by the one that appears in the charge correlator in n=4. So it is a product of the 3 vectors x mu. So it transforms covariantly as a vector at point 1, but neutral at point 2 and 3. And there's another like basic element I mu, which carries 2 pair of vector indices. And it also has the desired transformation properties at x1 and 2. So now in order to decompose these structures onto this basis of T1 and T2, of course, we can just compute this trace of sigma, this expression with sigma alpha dot sigma, 3 sigma matrices. And then we should be able to convert this expression into Lorentz notation. But we can also do it in a like kind of more quick way. So since we know we only need to fix two coefficients, we can always send as 1 point to infinity, 1 point to 0. This corresponds to a gauge fixing. So after doing, you can send x3 to infinity, x2 to 0, and x1 we place it at x. So therefore this left-hand side of this expression will simplify into this the simplified version, where you can already recognize that this corresponds to this g mu mu times x mu, if you transform it into the Lorentz notation. And for the right-hand side, if you send the 1 point to infinity, this T1 and T2 functions goes in the following case. But we will also simplify. So by comparing the left-hand side with the right-hand side in this special frame where we send 1 point to infinity, 1 point to 0, one can conclude that C1 is equal to C2 is equal to 1. So we can say we arrive at the final expression, which is this T1 plus T2 divided by some common denominators. So we have finished the computation of the 3-point function in coordinate space. So now we are ready to start computing the charge flow Q following these 3 steps that I already introduced earlier. One is the analytic continuation, and then you send the detector x2 to infinity, to the future null infinity. So this is not the same as if you're sending it to a infinity, but we pick a particular direction. I mean, we do the Lycombe decomposition and set only x plus infinity. So this is very different from what I did here by sending it to like this by treating all the component of the vector as infinite. So then we integrate over the retarded time, and then we do the Fourier transform into the momentum space. I think if you, I have explained how you do the calculations, you can practice as an exercise and homework for today, and to compute this this correlation function in coordinate space, and then do the Fourier transform. And for the Fourier transform, it is useful to use this master formula that I give here. And you will in the homework problem, you would encounter some tensor structure, some integral with tensor structure, for example, x mu x squared. And this integral can be obtained by taking derivative with respect to q on the integral, on the scalar integral. So basically, these are the only formula that you will need to compute the Fourier transform for the charge correlation. So in the end, if you do the exercise, you will find that the charge correlation in coordinates in momentum space will given by some factor like 1 minus cosine squared theta minus 1 cube factor. And in experiments, you can measure these charge correlations, and if you find an agreement, then that would probably confirm that the model that you built for the SU2 the electroweak model. But if you have like a anomaly which will come with the Z bosons, and you will get something that is proportional to epsilon mu mu rho sigma. Which are dotted with the polarization of the initial state current and the direction of the muse and the direction of the detectors. So if you find such terms, then that means you have the anomaly in your series, and which needs to be explained. Okay, so to summarize, we have introduced some techniques to compute the event shift from correlation functions. In QCD or in N equals 4, you can do, I did some calculations at Born level, but this approach can be generalized to loop level. And the key is to compute some loop corrections to the correlation functions. I do not have time to go into details of that, of the loop corrections in the QCD case, but this can be done by Feynman diagram calculations via Lagrangian insertion approach in QCD as well, just like the N equals 4. So that's all for today's lecture. Does anybody have any questions?
Thank you very much, Kai. Let's thank Kai for a very nice lecture. And yeah, we have 15 minutes for questions if anyone has any questions. Okay, if there are no questions, so I think Kai will also be arranging the tutorial today. Is that correct?
Yes.
Perfect. So there'll be another opportunity at the end of the day in case you come up with some questions in the next few hours. So we'll stop.